Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to knock out frame buffers and the synchronization objects. Really quick though, I would like to take a quick second and thank the partners of the channel, Eearslya and Wensheng. The partner is the highest tier of supporter on the channel. And so I just wanted to say thank you to our partners as well as our other supporters that are listed here on the screen. So if you're interested in supporting the channel, there are a couple ways to do that now. First off, I have channel memberships available. You can access that by clicking the join button below this video. I'll also provide a link to a video that I have describing the memberships. And I also have a Patreon page, which is patreon.com/Travis Vroman. Thank you all very much for your support. It is greatly appreciated. So before we get started, I'll briefly describe what a frame buffer is. A frame buffer basically has a reference to the attachments that are rendered to. So the render pass will need to know about the frame buffer, and the frame buffers are actually used to relay data back to the swap chain to actually render out images. So frame buffer is sort of the glue that glues all those things together, okay? However, even though they are the glue, they are actually pretty simple. So thankfully there's not a whole lot to actually touch on here. So let's go ahead and jump in by creating a new file. We'll call it Vulkan Framebuffer.h. And of course it includes our Vulkan types. And we have a Vulkan Framebuffer create, which takes a context, a render pass. This is the render pass that the frame buffer will be associated with. And then a width and a height of the actual images, the number of attachments, the views of those attachments. Remember, attachments are just images. And then an out pointer to our frame buffer object. Now we don't have this defined yet, so let's go ahead and create our Vulkan frame buffer in our Vulkan types. So underneath Vulkan render pass, we'll want to typedef a struct Vulkan frame buffer. It holds a VK frame buffer, which is the handle, the attachment count, the array of attachments, and then a pointer to the render pass that it is associated with. Okay, and that's it. That's all the frame buffer actually holds. So back here, we see that that error is resolved because we've created that structure. So naturally, anytime you have a create, you also have a matching destroy. So we'll go ahead and hook that up as well. Just takes the context and the frame buffer, right? And that is actually it for the interface of this, right? There's not a whole lot that you actually do with frame buffers. You really just sort of create them and use them. So next we'll create a new file. And we'll call it Vulkan Framebuffer.c. And in this case, we are going to include Vulkan Framebuffer and then K memory because we actually need to allocate some memory. So the first thing we're going to fill out is our create. And before we actually do any of that, we are actually going to take a copy of the attachments that are passed in here, right? So that we don't have to rely on this array still existing afterwards, okay? So we're going to dynamically allocate some memory for that, and we're just going to copy the values in, okay? And then we are also going to copy over the render pass that's passed in, as well as the attachment count, okay? So we're going to store all those things in our out frame buffer struct. And of course, just like anywhere else where we create something, we have a create info, right? So this is a create info for our frame buffer. And it takes a number of things. So it takes a render pass, which uses the render pass's handle, the attachment count, of course, the array of attachments that it is using, the width, the height, and then the number of image layers, which in this case is just going to be 1. And then we simply call vk create frame buffer, which takes in the device, create info, allocator, and handle. So it's the same pattern we've seen many, many times, and it just sort of keeps repeating itself, right? Which makes Vulkan a little bit easier to understand after you've been doing it for a while. Okay, so by proxy, the destroy basically just undoes all of this stuff. So we call vk destroy frame buffer, and then we say if there are attachments, we go ahead and just free that memory and set the attachments to 0. And then we also zero out the handle, attachment count, and render pass. And that's it. That's all there is to creating our frame buffers, at least from the interface perspective, right? So now we need to go to the back end and actually tie this in. So in the back end, all the way at the top, we want to include Vulkan Framebuffer. Okay, and our Vulkan Framebuffer is going to be created in a new private method, similar to how we have our create command buffers. We are going to have another method called regenerate Framebuffers, which is going to take the renderer backend, the swap chain, and the render pass, right? And this is basically what's going to hook all those pieces together. Okay. Now, why are we saying regenerate Framebuffers? Well, this method is basically going to do the initial generation of the frame buffers, but anytime you change the window size, you're also going to have to regenerate the frame buffers just as you would the swap chain, because the image size is actually going to change because the window size changed, right? And so there are going to be multiple events where we have to regenerate frame buffers as well as, you know, swap chain and all that other stuff. So when we actually implement window resizing, you guys will see what I mean. So we're going to do the generation and regeneration all in one place, and we're just going to call that regenerate frame buffers. Okay. So in initialize, we'll go ahead and set up the call to that first. So we actually want to do this right before we create the command buffers, right? So we're going to create what we're going to call our swap chain frame buffers here. Okay. And on the swap chain, we're actually going to have an array called frame buffers that we are going to set up a D array for. Okay. And then we are going to call regenerate frame buffers against that. Okay. Now, we do not have on the swap chain this frame buffers, so let's go ahead to our swap chain. Okay. And right below depth attachment, we are going to add to it our Vulkan Framebuffer array of frame buffers, right? This is just frame buffers used for on-screen rendering is what we're going to call it for now, right? So now that we have that in place, we've set up an array for our frame buffers, and we're calling our generate or regenerate frame buffers on that. So now we actually need to define regenerate frame buffers. So all the way at the bottom, we're going to define that function here, and we're basically going to iterate our swap chain images, because we need a frame buffer per swap chain image. So just like we needed a command buffer per swap chain image, we actually need a frame buffer per swap chain image, right? Because we needed separate frame buffer for each one of those things, okay? And so all we're going to do is we are going to create a frame buffer for each one of those, right? And here's where we actually set up the attachments, right? So we have an attachment count of 2, and then we're setting up our attachments. The first one is going to be the swap chain views, which is basically just our swap chain images, right? So that's the color attachment. And then the depth attachment is going to be the depth attachment image view, right? So here is the views that we're going to be using. And then when we call Vulkan Framebuffer create, we pass the context render pass, frame buffer width and height, the attachment count, the attachments themselves, which are just the views of the images, and then the frame buffer sub I, okay? And that is all that this does, right? The steps for generating and regenerating are exactly the same, and the array is already created outside of this, so we're just calling this regenerate frame buffers because we're going to call this anytime we need to sort of repeat this action, okay? All right, now, if we go back up to our initialize, if we go back up to our shutdown, obviously we will need to destroy these frame buffers. So since we're technically creating the frame buffers before we're creating the command buffers, this doesn't technically really matter in this case, but I'm going to keep it consistent and keep the order the same. Between the render pass and the command buffers getting destroyed is where I'm actually going to destroy the frame buffers as well. So again, we're just going to loop through those and call frame buffer destroy on that. Okay, and let's go ahead and build. And I just want to build and run really quickly to verify that this is all good. And it's not. You can see here we got some errors. So it looks like requested VK Framebuffer create info width must be greater than 0. So for some reason the width and height are not what we expect them to be. So let's see what I'll bet it's because of, so if we do regenerate frame buffers, right, let's put a breakpoint here and debug and see what we actually get. For some reason that did not actually break there. There we go. Okay, so we can see here that our frame buffer width and height is actually not being set, which is not good. So let's check and see where that is actually being used. So it looks like it's being used. We're actually only using it, but we're not setting it. So that's not great. Okay, so this is because we actually are missing a bit that we need to fill in to actually get that size, right? Because we're referencing the size, but we're not actually filling it out anywhere, right? Like there's nothing up here in our initialization that is actually setting up the frame buffer size, okay? So what we're gonna need to do is we're actually going to need to set up a call from our application, right? Because if you recall, our application config actually contains a startup width and height. And so we're going to use those as a default, and then whenever the window is actually resized, then we can update those things. But we actually need a way to get the frame buffer size from the application. So we are going to use a new method that we're going to create here called application get frame buffer size. Okay, and we're going to go ahead and declare that in the C file, and we're going to put that right above application on event. And all this is going to do is it's going to take the application get frame buffer size, and it's going to set the width to the app state width and the height to the app state height. Okay, and so those should actually be set based on these things here. So back in the back end, let's go ahead and call this application get frame buffer size. Okay, and we'll call that right here. Okay, that means, of course, that we'll have to include application. To that, we are going to pass a couple of static temporary variables that we're going to create, right? So we're actually right near the context. We are going to cache a frame buffer width and height. And these are going to be used until we actually have a replacement value for them from a resize, right? So we're temporarily going to use that. So we're going to pass the address of cached frame buffer width and the address of cached frame buffer height. Once we have that, then we're going to go ahead and set the context frame buffer width and height to that frame buffer width and height that are provided by the cached value, right? So if this happens to return 0, for example, then we're going to check to make sure that it's not equal to 0 before actually caching it, or before actually setting it. Otherwise, we're going to use 800 by 600 as a default. Okay, so this sort of gives us a safeguard to make sure that we're not using 0. Okay, and then we are going to reset at this point the cached frame buffer width and height back to 0. Okay, and you'll see when we go to resize how we're actually going to use those later on, but for now we're just going to leave that as is. Okay, so now we should actually have something that is a non-zero value there. So let's go ahead and build and run and get rid of the breakpoint. Okay, so our frame buffer width and height is 800 by 600. So it looks like it is using our defaults instead of what we actually pass in the application, which is not right, but we can actually fix that later. So it means our fallback is working, which is actually a good test. So I'm going to go ahead and remove these breakpoints and continue. And we see here that everything stood up correctly. So we do not have any validation errors here, nor in the debug console. So we are all good to go. So that means our frame buffers are generated properly. Okay, and let's go ahead and actually shut this down the proper way too. And we see here that we did not receive anything on shutdown as far as validation errors. So we're good to go as far as those are concerned. Okay, So that covers frame buffers. Okay, so the next thing that we're going to have to create is some synchronization objects. And our synchronization objects are going to be our fences and semaphores, okay? And if you remember, our semaphores are basically GPU to GPU, and our fences are application to GPU as far as synchronization goes. So we're going to need both. So we're going to go ahead and set up both, okay? So in our context, we are going to need to add a couple things. So I'm going to go back to Vulkan types, and we're going to add some things here to our context. So right underneath where we had our graphics command buffers added last time, we are going to add several new things. We're going to add 2 D-arrays of semaphores, okay? So the first is going to be image available semaphores, and then we have queue complete semaphores. And these are triggered by different things. So when we have an image that becomes available for rendering, that semaphore gets triggered, and that's basically where we're done presenting it. So it becomes available to be rendered to. And then we have the queue complete semaphores, which means a queue has been run against that and is now complete, and it is ready to be presented. Okay. And then we have the in-flight fence count, which is something that's going to be set once and sort of reused over and over, but we have to track how many of those we actually have. And then we, of course, have an array of those. And then we also have an array of pointers to Vulkan fences for images in flight. So this basically holds pointers to images which exist and are owned elsewhere, meaning that they're actually owned by this array, and these indexes are used with the current frame to keep track of what images are currently in flight. So these will either be set to one of these or they'll be set to 0, and when we hook up everything to the render loop, you guys will see what I'm talking about. But we're using this Vulkan fence structure that we do not have actually set up yet, so that is the next thing that we're going to have to actually do. So let's go ahead and create that, and that is going to be right above, we'll do it right above the context actually. We'll do it right here. And all this holds is a handle and then whether or not it's been signaled. And the is signaled is basically happens whenever we are waiting for a fence, and then that fence gets signaled because a operation has completed. We can use this to determine whether or not that has actually occurred, because this is just an opaque handle. So we'll keep this to determine the status of that fence. It's either signaled or unsignaled. It's a Boolean state. Okay. All right. So now that we have that done, we can go back to our backend, and we are going to go ahead and create our sync object arrays. So we'll go up to our initialization. After our command buffers, we will create arrays for our sync objects, right? So 2 for semaphores and 1 for fence, right? So those are the D arrays for that. And then what we're actually going to do is we are going to loop through the max frames in flight, right? And we're going to create a semaphore for each one of those things, and we're going to create a fence for each one of those things, okay? And I realize that we haven't created this Vulkan fence create yet. We'll get to that in a second. Okay, so this first one, of course, creates a semaphore in the context image available semaphore sub I, and the second one does it for queue complete semaphores sub I. And then, of course, this is creating a fence at context in-flight fences sub I. Okay, so we have this Vulkan fence create. We probably ought to go ahead and set that up next. Okay, so to do this, we're actually going to need to create a new file, and we're going to call it vulkanfence.h, as you may have suspected. It, of course, is going to have our normal include at the top. We have a create, which basically takes a context, whether or not it should be created in a signaled state already, and a pointer to the out fence. So there are situations where we're going to want to create the fence to say, hey, this has already been signaled, don't wait on it, right? And we'll actually have an example of that very soon. So we need a Boolean to sort of give us that flexibility to tell us whether or not we should create it that way. Of course, we have a create, so we have a matching destroy pretty self-explanatory stuff. Next, since a fence is something that can take a certain amount of time, we actually need a way to wait on a fence. And so this is what that is going to provide. It's going to say, we want to wait on this fence and then have a maximum timeout in nanoseconds of whatever is passed in here, okay? And so the last thing we're going to need is a fence reset, which basically resets the fence signaled state to be false. And that's all it does, right? So this here is a blocking function. It's it waits on this particular fence, either for the operations that the fence is waiting on to complete or for this amount of timeout, okay? And then returns true or false based on those results. Okay, so obviously, since we have an H, we need a C for our implementation. Okay, and in this, we just need the fence and the logger H files. Okay, and so in our create, the very first thing we're going to do is we're going to copy over the is signaled to create signaled, just so that we have that state actually saved correctly. And then of course, we are creating a fence, so we need a create info. This create info doesn't really contain much of anything. In fact, it only contains the structure type, a pnext, and flags. Okay, so really all we care about is the S type, of course, and then we also, if the fence is signaled, then we'll set the flags to say, hey, create this already signaled, right? And that's where this comes into play. So when we actually create this, this fence flags will be 0 unless we have signaled it, or we're creating it signaled, and then we're going to create it using this flag. Okay, and then from there, it's just a VK create fence. Pass the device, create info, allocator, handle, standard stuff. Okay. Destroy is also pretty simple, as you might expect. If we have a handle, call destroy fence on it, pass the handle, the allocator, the device, set the handle to 0, and then set is signaled back to false, just because that's sort of the default states of fences most of the time. Okay, so the next one is this Vulkan FenceWeight function. And basically what this is going to do is, if the fence is not signaled, then we're going to wait, right? If the fence is signaled, in other words, we meet this criteria down here, we're going to return true, because if the fence is already signaled, we don't need to wait on it, right? So we can just immediately boot out of this, okay? If the fence is not signaled, then that means that we need to have some sort of wait on it, right? And so this one we actually want to pick apart a little bit in terms of how we actually do this. So we're going to call VK wait for fences, which can actually wait on more than one fence. We're going to pass it the logical device, say that we're waiting on one fence, pass it the fence handle, and then this true is actually for this wait all, which is basically saying we want to wait on all fences that we pass, which is true. And then we're also going to pass it the timeout along here. And so this result can actually return some interesting things that we care about. So we actually want to switch on that result, right? And that switch looks something like this. So if it's a success, then we want to say the fence is signaled to true and return true. Okay. If it timed out, then we're gonna want to warn about that. We're gonna say, hey, this timed out. Okay. If the device was lost for some reason, then we're gonna report that. If we're out of host memory for some reason, out of device memory for some reason, or we receive some sort of unknown error, we're actually going to report that relevant thing here. And then all the way down here at the bottom, if we hit this, that means we fell through somewhere here, and we have a failure case. So we would return false here. So long story short, this Boolean here returns true on a success, false on an error. Okay, and so again, if the fence is signaled, and then we wait on that fence and it comes back a success, it returns true. If the fence is signaled, it does not have to wait, and so it returns true because that's still a success case. Otherwise, it returns false. Okay? And then, of course, we need a way to reset the fence. So if the fence is signaled, then we need to call VK reset fences, which, again, can accept more than one, but we're only passing one, so we're saying 1, and then the address of the handle, and then reset the fences is signaled to false. And that is all there is to Vulkan Fence. So back in our backend, we will now have this Vulkan Fence create if we include that file. So we'll go back to the top and we will include vulkanfence.h. And now we have that. Great. So now we have our semaphores and our fences actually created. So the next thing that we need to do is we need to set up our images in flight array. Okay, and this is for images that are currently being rendered to. And so what we're going to do is we're going to create this array, right? Because we still need to represent space for it, right? And we're going to loop through it and we're going to set everything to 0 because nothing should be in flight at this point. So a cleared list is basically all of the entries within that array are 0. And basically it will be 0 when not in use, right? So this comment sort of explains everything that's going on here. So the actual fences are not owned by this list, so we do not manage them in this list. It's merely a pointer to the images in flight. Okay? All right. So that is it for the creation. As far as the shutdown goes, we actually need to destroy these things. However, to be on the safe side, we want to make sure that there are no graphics operations being currently executed when we go to actually shut down. So we want to go ahead and very first call this VK device wait idle. And this will basically wait until the device is not doing anything at all. And that's because if we try to destroy stuff while we're actually using it, we'll get errors, and we don't want that. So we call VK device wait idle just to be safe, on the safe side about that. Next, we're going to destroy our sync objects. So we have another loop here where we go through our max frames in flight. And for each one of those, we destroy the semaphores, the image available semaphores, and the queue complete semaphores. And then we also destroy our fences, right? Because there will be the same amount of all of those things, right? And so while we're at it, we then also, once we've cleared those objects out, we need to destroy the arrays. So we have the destroy of image available semaphores, the destroy of queue complete semaphores, the destroy of in-flight fences, and finally the destroy of images in flight. Okay? And that should pretty much do it for the destruction. So let's go ahead and build, and we'll go ahead and run. And we're running here. I don't see any errors here, so I think we are good to go. Let's check the debug log. There's nothing in here. Okay. And we'll go ahead and exit the application the normal way and check this again. And again, we do not have any validation errors. So we've actually we've done everything properly up to this point. Okay. So there is one more thing in the swap chain code that I forgot to add that really should be added, and that is in the swap chain present. There is another line down here at the bottom of it where we need to increment the current frame index. If we don't do that, our loop in a bit is not going to work correctly. So basically, this is taking the current frame, incrementing it by 1, and then modding it against the max frames in flight. So basically, it will just keep incrementing that loop and then wrap it around back to 0 whenever that is over the max number of frames that we have allowed. So we'll want to go ahead and get that added as well so that that works when we go to call it. Okay. Anyway, that is going to do it for this video. So in the next video, I believe it is actually time to glue all this stuff together, start issuing commands, and get clearing to our screen. So very exciting stuff. We're actually going to have a visual update on our engine for the first time in quite a while. So I hope you guys enjoyed. I hope you guys are learning, and please toss the video a thumbs up if you liked the video. If you haven't already, consider subscribing and click the little notification bell there to get notifications as to when the next video in this series drops, and I will see you guys next time.